Okay, so we have a beam of spin half particles, and we have it in this state. And it says, what are the possible results of a measurement of the spin component as Z, and with what probabilities do they occur? So just to give you a hint, we know that the spin components in the Z direction are either going to be a half or a minus half, meaning h over 2 or minus h over 2. Okay, so it can either be h over 2 or minus h over 2. This is the SZ, the Z component. Okay, so this is spin down, and this is spin up. Okay, so and now you need so these are the possible measurements. Okay, these are the possible measurements. It's either gonna be sorry, by the way, this is h bar over 2. Okay, for spin up and spin down. So these are the possible measurements. Now, how do you find the probabilities of these measurements? Again, you do sort of the same thing. I'm gonna give you a hint, and then I'm gonna let you continue this, because now I think you should be able to do this, because it's kind of what we did in just a different format. Okay, so so for the probabilities, okay, so if you to find the probability, okay, of it being in the h over 2, right? So look how you interpret this. Okay, let me show it to you calculus way, and then I will turn it into a bracket notation. Okay, so calculus speaking, what we have to do is we have to take the wave function, okay, and we're gonna have to operate on this with so the wave function is in, okay, so whatever state it's in, that goes as your cat. Okay, and the state that you are trying to find the probability for, that will be your bra on the left. So that would be the, since h bar over 2 is the spin up, that's going to be, remember, we denote this by this, but we don't usually write 2 lines, we just erase them for convenience, we just keep it 1 line, right? And then we have to square this. You understand? This is your probability of finding this in the spin up state. So you want to take it from here, because from here it's very similar to what we just did. Do you want to continue now and try it yourself?
Yeah, I think
because psi, you have psi, plug it in.
Yeah, it's h bar over 2.
Yeah, and then operate on, yeah, it's whatever up there. No, psi is the question. Psi is this. Psi is this.
Right.
Yeah, plug it in and then operate on it with the bra and see what you get.
Alright.
This is part of where quantum mechanics is weird, is because you do have the state that you're in, but once you make the measurement, you're not guaranteed that you're going to get the same thing. The state of the system will change. So the measurement collapses your wave function into a single outcome. And that's what you're finding is in the current state of the system. Yes, it's the probability of being spin up is 2 over root 13, and then spin down is the other part. But then once you make the measurement, this is going to change, and it's no longer it necessarily have to be 2 over root 13. In fact it's almost certain it isn't. Okay, watch. You just plug in psi. So after the step is equal, you just plug in psi, okay, from the question. So what's psi? It's 2 over root 13. Just copy it down. So in the place of this, you plug in this. Plus I 3 root 13. This is that step. Okay, I'll let you do the third. Now you're gonna take the inner product.
And that was crap, I forgot what the inner product was. I thought I knew it from
Think of it like algebra. It's like you're foiling this state on this state, then this state on this state.
Yeah. Oh, okay.
So what do you get from the first state?
Yeah, you get plus 2 over root 13.
You get exactly. You get plus 2 over root 13 because spin up is 1.
Minus I over I, 3I over I times 3 over 13.
Nope. What's this? What's the answer for this inner product?
That would be plus.
No, look. This is spin up, spin down.
Yeah, right.
What's this equal to?
That would be 0.
0. This goes away. So it's just 2 over root 13 squared.
No, down on the left side.
So just 2 over root 13 squared. So that means the probability being in spin up is actually 4 over 13. Okay? Go ahead and try now the other probability, the spin down. Because you have two. You have spin up and spin down. So you want to try the second one?
Oh, and then that would be...
So I'll let you try the second one. So the second one, so now you're doing P minus H over 2. What do you expect the answer will be?
Well, there is a minus component inside, so it's not going to be 0, right?
No, it's not going to be 0. Look, think about it. It's 100% probability distributed on two outcomes. If one of them is 413, the other one will be 1 minus 4 over 13.
Oh, well, yeah, right.
Which will be 9 over 13. But why don't you go ahead and do it explicitly? That way you can learn the process. Like do it like I did it. Like take the inner product of that state with the wave function, with the current state. When you take the okay, so for this part you're gonna get so this is the minus h over 2, right? You're gonna get the minus over the wave function, and if you do the same thing we did above, you're just gonna get the second state to survive, right? So and then squared, of course. So you're gonna get I 3 over root 13 like this, correct? This doesn't mean you're squaring it because there's a complex conjugate there. This means you're multiplying by its complex conjugate. So this is, so yeah, this is gonna show up a lot, so make sure this doesn't confuse you. This is saying I 3 over root 13 times minus I 3 over root 13. That's what it means. And indeed you will get 9 over 13 because I squared is minus 1.
Wouldn't the complex conjugate of that be I times, wouldn't it be I times 3 over 13 plus or minus,
No, look, the complex conjugate, look, I know what you're asking. I think I understand what you're asking. The complex conjugate of A plus BI, okay, is, yes, you're right, it's A minus BI.
Oh, yeah.
Okay? But here you don't have a real part. It's just BI. What's the complex conjugate of BI?
Oh, just minus BI.
Minus BI. Because A is 0. So the complex conjugate of this is minus BI.
Oh, yeah, because A is 0.
Yeah, because A is 0.
Right.
Because, see, if you don't take that into consideration, you're going to get a negative probability, which doesn't make sense.
Yeah, because there's an I there.
And mistakes of this nature will be even more dramatic on other things. Here it just basically like makes your probability negative, which is definitely wrong, but I'm saying on other things it makes worse outcomes than this. So part B, it wants what are the possible results of the measurement of the spin component Sx now? So now you're doing the X matrix, meaning the component of the spin in the X direction, and with what probabilities do they occur?
X. Okay.
Yeah. So what are the possible measurements in the X?
These are in the Z direction.
We did the Z. Now it's the X.
Yeah. So then,
Same thing. This is a half spin particle. The possible measurements are still H half.
oh well, yeah. The magnitude.
Right. So H bar over 2 for spin up, and minus H bar over 2 for spin down. Okay, now for the probabilities, it's going to be the same thing. You're going to take the inner product, but you're going to be using the Sx matrix instead. It's a different spin matrix. There's 3 different matrices: Sx, Sy, Sz. It's in your book.
That doesn't indicate
No. If what you're asking me is why would the outcomes be different? Yes, the outcomes would definitely be different because
because it's a different direction. But the wave function originally didn't indicate whether or not it was like what X, Y, and Z components.
Yeah, I know, and that's why here. So the way that you're doing this book is kind of putting this as a recipe, and you just use it as is. But basically, what really happened here, there's some work that happened in between, where you have to actually use the Pauli spin matrices, which are different for the x, y, and z. And what those spin matrices are is when you find the eigenvalues, right, and the eigenspinners for Sx, they turn out, for the spin in the x, they turn out to be quite different from the eigenvalues and the eigenspinners in the y and the z. And the reason, I mean, it all goes back to the fact that when you solve the differential equations for the angular momentum, you just get different eigenvectors for s squared as z x y, actually s squared, yeah, for s squared as z s x and x y, and in fact the sx and the sy, you'd have to use it's kind of you'd have to construct the matrices from S plus and S minus for these, and so and then when you do all that inner work, you come out with these eigenspinners for Sx. We call them eigenspinners, except that here they're in the bracket notations, in the ket notations, rather than in the matrix notation, right? But yeah, I mean, the possible measurements are indeed the same, but then the Pauli spin matrices from which you derive those Sx, Sy, and Sz are not the same. That has to do with the fact that the spin values are not the same from solving the angular and radial differential equations of the wave function in the first place. Don't give you the same result for all three of them. If you know what I'm saying. And by the way, all this discussion here was on the spin half particles. I mean, it applies in general that they'll be different, but I was referring more to the spin half particles. You understand? So knowing the spinners, you could actually derive the matrices S squared, Sz, S minus S plus, and then from there get Sx and Sy from taking the average. But yes, they're all different, and these are the results that you're going to use. So in this question, so now down to this, it's the same. Now that you know this, it's the same thing as you did before. So the probability, right? You're gonna get that it's what was the question saying? Plus x and minus x, right? So the probability that it's plus x, you have a function in this state, and you're gonna operate on it by this. Okay, so by basically this, except you're gonna turn it into a, first we could write it out. Okay, and we are talking about the x here, and then you just plug it in, and you take the complex conjugate of that, right? which will be the same because 1 over root 2 is real. So this will be 1 over root 2 plus spin down, and then now for psi you just plug in psi. Psi is the question, the state you're in. 2 over root 13, right? Two over root 13, and then I 3 over root 13. There you go. And now do the inner products like we did before. I'll let you do the inner products. Let me know what you're getting. Oh, by the way, I forgot a 1 over root 2 here, because 1 over root 2 is foiled on both of them, on this and on this. Yeah, and by the way, I also forgot another thing. We have to square this, right? Because remember, it's probability can never be negative.
Right. Well, wait, are you sure we're squaring this? Because isn't multiplying that by that getting rid of the radical?
First, you do the inner product, then at the end, you take the module, which is whatever answer is times its complex conjugate.
So is that really, instead of squaring, is that really what we're doing?
Yes, that's what we're doing. We're turning something that may not be real, artificial and imaginary, into something that's real. Because remember, in quantum mechanics, when you plot the wave functions, the wave function can actually go below, can be negative, right? Because the wave is sinusoidal, sines and cosines. But when we do probability distributions, we square the probability is actually the square of the thing, so that we can eliminate the negative.
Physical sense.
Yeah, so that it makes physical sense. Yeah, exactly. Well, let's see. Look, follow here. Follow me on the pad. So we have right, we have this. When we operate with this on this, we get 1. So we get 2 over root 26, right? Are you following me on the pad?
Yeah.
Okay, and when we operate with this on this, what do we get? You there?
Yeah.
When we operate with this on that, spin up on spin down,
We get 0.
this is 0. This is 2 over root 26. And when we operate, let's change colors here. When we operate with this on this, what do we get?
We get 0.
0. And then this on that, we get just the numbers, yeah? I 3 over root 26. So 3i over root 26. So, right? So this is plus 3i over root 26.
Yeah.
And this is supposed to be modulo square, yeah? So that means it's going to be 2 over root 26. Are you following?
Yeah.
Plus 3i over root 26 multiplied by the complex conjugate of this. What's the complex conjugate of this?
That minus.
Yeah, just the same minus. Yeah, exactly. So, and then just take the difference of two squares, right? And you get the answer. So this is just square the first minus square the second, yeah? So this is 4 over 26 minus, now I squared is minus 1, so this makes this a plus, 9 over 26.
Yeah, and that gets to 1/2.
That gets to 1/2. So that means probability being spin up along the x is half. And you could do the same thing for the spin down, but it's obvious it's going to be 1 minus 1/2, which will be 1/2. The other one, right? But it's the same process. You just use this spinner here.
I guess it does make sense, because if the spin is along the
Now, you have to be really cautious with using intuition with quantum mechanics. It's very counterintuitive. It doesn't always work.
Although it actually not like what's the problem?
Yeah, and yeah, so that's why for part C, when you plot these, you could actually see it, yeah?
We're not trying to find the probability that it's along a unit vector.
So when it was minus h bar over 2 versus h bar over 2, right? What did we get for minus h bar over 2? We got 9/13. So we got something like this, yeah? And let's say here this is 9/13. This is the probability axis. And the 4/13th, so if this is 9 dashes, you would do 4 dashes here. 4/13th. That's for a Z. And for SX, they will be evenly spaced, correct?
Right, yeah.
So we get half-half.
Actually, this could be.
This is the histogram that it's asking about.
Right, and then if we did another one for y, then we could.
So this is minus h bar over 2, and this is plus. These are the possible measurements, and the histogram shows the probabilities.
Yeah, and then if we did another one for y, we could get.
No. Here's a misconception. People think that this is a short. This is a it's a pitfall because it has to do with a discrepancy in measurement. It has nothing to do with the accuracy of the measurement. It's inherently built into the nature of the system, and that's what makes it really weird.
Well, what I was saying